Hi there. This video is a review of integration from Calculus 1. I have three goals or outcomes for this video. The first is to explain the connection between these calculus symbols, so this thing right here and this other one over here, and how these things are related is called the fundamental theorem of calculus. The second goal is to use the antiderivative shortcut formula to find integrals. And lastly, using geometry to find or estimate definite integrals. All right, let's get started with some examples on the first learning outcome. So we're supposed to explain the difference between these two, calculus symbols. So let's first of all explain what each of them mean. So this one on the right, this one right here, represents the antiderivative function. In other words, this thing represents a function. If we use a lowercase f of x in the formula, then we often denote the antiderivative as a capital F. So lowercase g would be capital G. You don't have to do it that way, but that's often the way it's written. What does the antiderivative mean? It means when you differentiate this antiderivative function, this capital F of x, you get the lowercase f of x. So the antiderivative is the function that when I differentiate it, I get back to the original function in the statement. All right, what about this other thing right here? Well, this is also called an integral. If you want to differentiate between the two, mathematicians don't always differentiate between the two, but if you'd like to, this first one is called an indefinite integral. And the second one uses the adjective definite integral. Sometimes that helps distinguish between the two of them, but as I said, mathematicians are kind of sloppy when they describe these things, and they tend to call them the same thing, integrals. So what is the second thing? Well, it has the AB on there. That's the significant difference. And that is going to be the area, the signed area between the function and the x-axis and between x equals a and x equals b. The reason why we call it a signed area is because if you're below the x-axis where the y values are negative, you're going to end up with a negative area, and we'll be able to interpret what that means later on in this course. So this thing, AB fx dx, is not a function. It's a number. It's like 7, the area is 7 or something. So this definite integral with the AB on the integral sign results in a value, or the area between the function and the x-axis and between x equals a and x equals b. So what does the fundamental theorem of calculus say? Well, it says that these two are connected. If you want to find the area, between f of x and the x-axis and between x equals a and x equals b, the way to calculate this area is to actually find the antiderivative function first, plug in the values of a and b, which are the endpoints of our region, and subtract. And it's quite a marvelous thing. Calculus was being done for a couple thousand years before anyone realized this was a formula. So it's quite remarkable, and thus called the fundamental theorem of calculus. All right, let's go on and look at some antiderivative problems. All right, so for this problem over here, let me zoom in a little bit. It's asking to use antiderivative shortcut formulas to find the integrals. So the antiderivative formulas, the antiderivative shortcut formulas are things that you would have learned in Calc 1. I put a reference sheet of them on our Canvas page. So this is the reference sheet I made up, where it lists a whole bunch of those antiderivative formulas. If you don't remember all of them, feel free to have this handy when you're doing your work. And you can see the way I've organized this list is the more common ones are at the top, and the ones that you use less frequently are towards the bottom. So it's kind of, helps you find things if you're looking for the formula. All right, so like number 1 and number 2, we're going to be using number 2 quite a bit today. The antiderivative of x, which is a variable, to a number n, and you have to have a dx here. I know the dx doesn't sound that important right now. It's just like something you have to write, but trust me, it'll be very, very important and invaluable as we do more complicated integral problems in this course. So try not to neglect the dx. In this case, if you have an antiderivative with the variable x to the n dx, you get this little formula right here. All right, so let's see how that's applied for these example problems. So for example A, we have the integral or the antiderivative of pi divided by the sixth root of x. Let me make that just a little bit bigger in case your screen is small. Okay. So we're going to try to do the antiderivative. Now, you may remember from a previous video that math doesn't work very well with these roots and radicals and things like that. We need to actually use numerical exponents. So we're going to rewrite this thing or simplify it. We're going to simplify this as pi and then x to the minus 1/6 dx. The minus 1/6 comes from the fact that it's a reciprocal. That's a negative exponent. And the sixth root is written as the 1/6 exponent. So knowing how to simplify these roots into actual numbers like negative 1/6, kind of important. Now, constants like pi are not going, when they're multiplied by a function, they don't affect the derivative, nor do they affect the antiderivative. So some people, if they look at a problem like this, they'll even write the pi on the outside. You do not need to do this, but you'll see this oftentimes in that they just say, you know what, because it's a constant being multiplied, I'm just going to focus on the rest of the problem and multiply my answer by pi at the end. Let me remind you of that formula on the formula sheet. If I have x to some number dx, the antiderivative is x to the n plus 1 divided by that n plus 1 plus a constant, which when you differentiate, it goes to 0. We need that plus c in there. All right, so let's go ahead and finish up this problem. We get pi times the antiderivative of this thing. I have to add 1 to the exponent. Negative 1/6 plus 1 is 5/6. And I divide by 5/6. That's the x to the n plus 1 over n plus 1. And plus c. I am going to want to simplify this a little bit. Divided by 5/6 is times 6 over 5. So I can write 6 pi over 5 x to the 5/6 plus c. And that's my antiderivative or the integral of the formula in part A. All right, remember, you can pause the video at any time and give these a try. You don't always have to watch me solve all the problems. So I invite you, if you want, to try part B. I gave a little hint over here on the side. And if you get all the way through, that's fantastic. If you get stuck somewhere, at least you know where you got stuck and you can watch the video to see how to get unstuck. That's always a good way to increase your active learning, is to pause the video and give these a try. Well, whether or not you pause the video and come back, I'm going to do example B now. So for example B, we have the quantity 2x plus 3 all squared. We're trying to find the antiderivative of that thing. There is a chain rule. If you remember your derivative formulas, a lot of people remember the chain rule in derivatives. There's also something called the product rule in derivatives. And so some people are thinking maybe this is a chain rule problem or product rule problem. I need to be clear. This is an antiderivative problem, and there's no product rule in antidifferentiation. There's no chain rule in antidifferentiation. There are things that are kind of like that, but not really. It's just kind of a different critter. So you can't really use those rules or those ideas from your derivative knowledges onto your integral problems. So how do we do a problem like this? Well, the big theme for doing antiderivative problems in Calc 2 is to simplify. Anytime we end up with a complicated expression, and this is complicated because if you look on your antiderivative formula sheet, there's nothing like this. There's nothing with parentheses in there and things being added together to some power. It's not one of the shortcut formulas. So we're going to have to simplify anything that doesn't look like one of our shortcut formulas, so then we can use our shortcut formula. If we can do some simplification, some math, and make it look like this x to the n formula, then we know how to antidifferentiate it. So that's the goal. And there's going to be some pretty sophisticated methods of simplification that we learn in Calc 2. We've learned one of them, or at least most people have learned one of them in Calc 1. It's called integration by substitution. That's just a technique to simplify a problem so we can anti-differentiate it. The next video that I'll present is a review of integration by substitution. So look forward to that if you need a review on that technique. Well, besides integration by substitution, which is a simplification technique, what other simplification techniques might we have learned in Calculus 1? The answer is algebra. We know you can use algebra to simplify things, and we're going to be using a lot of algebra to simplify our expressions. 2x plus 3 squared means 2x plus 3 times 2x plus 3. It means this thing right here. And if you multiply 2x plus 3 times 2x plus 3, which you have to distribute or FOIL, whatever you want to call it, you end up with 4x squared plus 12x plus 9. And this is dx like this. So what's nice about antidifferentiation is that if different parts are added together, you can integrate them separately. So I could actually integrate this as 4x squared dx plus a 12x dx. That's a plus there, plus 9 dx. So I can just find the antiderivative of all three of these things and then add together results. Works with subtraction and addition. Not with multiplication, unfortunately, or division. Those are not rules for antiderivatives. All right, once again, you can move the 4 on the outside if you don't want the 4 there because it's a constant. I typically don't care too much. So I'm going to antidifferentiate the x squared, of course, using our formula up here. And so I'm going to get 4 times x to the 3 over 3 plus some constant. And then we have over here, the antiderivative of 12x is 12x to the 2 over 2, because that exponent is 1. And we get plus c. Now, these c's can be different, so we have c1 and c2. And this 9, antiderivative of 9 is just 9x. Remember, the derivative of 9x is just 9. And I get some other constant. Now, there's no reason to write lots and lots of constants. You could just combine them all together as one constant. So there's no reason to write like lots of C1s and C2s and C3s. You could just wait for the end and add just some big C and say that's the constants from wherever you have the problem, right? So let me just clean this up a little bit, and that'll be the answer to part B. We get a 4/3 x cubed. 12 divided by 2 is 6, so 6x squared. And we get a 9x and a plus c. So that's our answer to the second question in the review of antiderivatives. All right, so for part C, I actually have the same formula as before, but it is a definite integral because there's a 0 and a 1 here. So the way I'm going to, or the answer I'm going to get here is going to be a number. And the way I'm going to compute that is by using the fundamental theorem of calculus, which means I'm going to find the antiderivative. So I'm going to find the antiderivative big F, assuming this is our little f, if we call that our little function or regular function. The big F would be the antiderivative, and then I evaluate it at the 2 endpoints and subtract, and that will be the area. Quite a lovely little formula. All right, well, we need the antiderivative formula, but the antiderivative formula is the one we just found. It's this one over here. In part B, we found the antiderivative formula by using some algebra to simplify and then doing the antiderivative of each of those parts separately. So what we can do is to find this definite integral, this area, what I can do is I can just take this expression, 4/3 x cubed plus 6x squared plus 9x plus c, and I can plug in the value 1, and I can plug in the value 0. You may have learned this from your Calculus 1 class. If not, I'll teach it to you now. This line with a value down here, like x equals 1, that's the way mathematicians say, take this expression and plug in 1. So I could do this thing, and I could do the same expression, plus c, and I could evaluate it at x equals 0, right? And that would be like one way of showing that I'm going to take this antiderivative function, plug in 1, plug in 0, and subtract. Math people hate writing so much, so they even have an abbreviation for this abbreviation. They will take this line here that you may have seen before, and they'll write both numbers here, x equals 1 and x equals 0. the top number on top, the bottom number on the bottom, and that denotes that we should find evaluated at 1 and evaluated at 0, and then subtract the results. All right, so when I plug in 1, I get 4/3 times 1 cubed plus 6 times 1 squared plus 9 times 1 plus c. So that's when I plug in the 1 value. And I'm going to plug in 0. You're going to see a lot of this is going to be 0 because 0 cubed is 0, etc. Looks like I need a little bit more space. Okay. Plus 9 times 0 plus c. When you're doing your own work, you don't need to write all these steps. A lot of people saying, why are you writing this out? You know that 1 cubed is 1 and 0 cubed is 0. Like, why write all these out? I'm just doing it just to help people see all the steps, just so that I don't lose people who are learning all this stuff and needing a reminder of how that all works. So you certainly don't have to show all the steps that I'm showing here. All right, so this ends up being 1/3 plus 6 plus 9 plus c, and they get a minus 0 and a minus 0 and a minus 0 and a minus c. And you'll see that there's a positive c and a negative c, and those will add to 0. A lot of people say they cancel. I'm not a big fan of that word. They add to 0. That's why we don't write them anymore. You can say cancel if you want. I'm just going to say that they combine together to equal 0, so we don't have to write it anymore. All right, so we get 1/3 plus 6 plus 9, which, we can write as 15 and 1/3. Or if you want to be a little bit more mathy, you would write this as an improper fraction. 15 times 3 is 45, so 46/3 would be the typical way a math person would write it, as an improper fraction instead of as a mixed number. I'll mark both of them correct, but that is the answer to part C, where we're asked to find the area. The area between this function and the x-axis, between 0 and 1, is equal to this number, a little bit more than 15. In other words, if I was to graph this thing, and I had the function 2x plus 3 squared, which is something like this, and I had between x equals 0 and x equals 1, so 0 is over here, 1's over here, this area right here, assuming that I graphed everything to scale and measured everything, that area would be about 15 and 1/3, or it would be exactly 15 and 1/3, or 46/3, as a matter of fact, not almost, but precisely. Okay, so that is an example of doing a definite integral by using the fundamental theorem of calculus. All right, our last objective is to use geometry to find or estimate definite integrals. So in this particular problem, I have a function, or at least the graph of the function below. I haven't given you the equation, and finding the equation isn't really the idea here. We want to use geometry to see if we can find the definite integral. Remember, this definite integral means the area between the function and the x-axis. So our function is this sort of line segment thing, kind of broken up into down, cross, up. And then this is between x equals 2 and x equals 8. And excuse me if my drawing is kind of small. Let me zoom in a little bit more. I don't think I can zoom in too much more. Here's x equals 2. And here's x equals 8. So if I was to draw like the endpoints 2 and 8 to the function, I couldn't really go 8 up because the function doesn't go up. The function goes down. So I'd have to draw it here. And the area between the function and the x-axis would be this area right here. Let me choose a different color. That area right there. And this area right here, that's the area between the function and the x-axis. So we need to find that area there. And because the second part, this trapezoidal part on the right, is below the axis, we're going to have negative y values, like -2. And this area is going to be negative. And the part on top, where y are positive values, is going to be a positive area. And the way we're going to calculate it is not by using antiderivatives. We're going to calculate it using area. So you have to use your geometry facts a little bit. This first area right here, this positive part right here, looks to be like a triangle. I need to find the lengths. This is 2, this is 3. So between 2 and 3 has a length of 1. And this is 0, and this is 2. So this height here is 2. And the formula for a triangle is half of a rectangle. So 1/2 times length times width, or base times height if you want. So in this case, it's going to be 1/2 times the 1 times the 2, or that's equal to 1. That's just for this little first part right here at area of 1. Let's look at the other area. This is an area of a trapezoid. Some people remember their formula for trapezoid. If you don't remember the formula for trapezoid, feel free to break this up into a rectangle plus a triangle. And then you can find the area of the rectangle, the area of the triangle, and add them together. So that would be one way of doing it if you don't remember the area of a trapezoid. The area of a trapezoid is the average of the bases. So not the longer base, not the shorter base, the average of those two bases. And times, the 1/2 base times height thing. So we need the height here. So 1/2 the average of the bases times the height. So on our particular problem, or that is the average of the bases. I think I'm saying it wrong, but I think you have the idea. So I take the average of the bases, which is 1/2 b1 plus b2. In this case, I need to find out the lengths of these two bases, and I need to find the height. So this bottom part right down here goes from, I can't read that very well. That's 4. It goes from x equals 4 to x equals 8. So that's a length of 4. And this top part here goes from here, which is 3, all the way to 8. So that distance is 5. And the height goes from 0 to -2. So that distance is 2. Now our answer is going to be negative because we know that we're using negative y values. But when we're using geometry formulas, we just consider everything positive. And then we can worry about the signs afterwards. So our bases are 5 and 4, and our height is 2, and so we get a total of 9. So our total area is going to be the area of this green shape plus the area of the blue shape. But remember, this blue shape is going to have a negative area, so this is going to be a -9 because it's below the x-axis. So that means this integral, I guess I should write down below, this integral from 2 to 8, which means the area between the function and the x-axis from x equals 2 to x equals 8 is equal to, well, 1 plus -9, which is -8. So that's the area for this problem right here. All right, so that ends the video. Hopefully this was helpful, and hopefully you will reach out if you have any questions or have any what-if scenarios or need help with anything else related to integration or anything else that you're working on in the class. Thanks, and I hope you have an enjoyable day.